DKW Physics. I'm Mr. McConley, and today we're going to continue our modern physics talk by talking about radioactivity. And radioactivity is the spontaneous decay of a nucleus. Can't even say the word. So basically, if you think of a nucleus has positives in it. And if you remember what we talked about with electrical charge, positives don't like to be near other positives. So in theory, if you just have a bunch of positives in one spot, they should all just push apart and, they shouldn't stay there together. But there's buffers in a nucleus, and these buffers are called neutrons. And these neutrons kind of act as a way to stabilize the nucleus so that the positives aren't pushing right up against one another, and the nucleus can be a little bit more stable. However, there's certain configurations or certain numbers that are more stable than others. And so what happens with radioactive elements is that the configuration is not very stable, and so the nucleus spontaneously starts spewing off pieces until it reaches a more stable configuration. So if you took chemistry, you realize that there are disintegration charts where they say it starts at this element, and then as pieces are spontaneously emitted, it drops down to this element, etc. So that's kind of a quick review of radioactivity. And we're going to approach it from a little bit different angle in physics. First of all, Henry Becquerel in 1896 was the person who discovered natural radioactivity. Now, past that point, a lot of people studied it and played with radioactive material in order to try to figure out how it works. And most of these people did not realize it was at all dangerous to them at the time. So you can imagine that they were getting exposed to a lot more radioactivity than they probably should have. But one guy I want to highlight first off is Ernest Rutherford. Ernest Rutherford did a couple really nice experiments, and one of them you've already talked about in chemistry, but I'll review it real quick, is the gold foil experiment. He took radioactivity and he pointed it at a thin gold foil, and when he did that, you recall what happened?
Most of the particles that came from the radioactive source went through, but some...
Most of it went right through. So what he was proving by that experiment is that most of the atom is actually empty space. The majority of what makes up an atom is empty space. And that was a really good experiment, and there was more he learned from that, but that's the main thing. Now the other experiment he did was basically, he took a chunk of lead, because at this point they realized that lead didn't seem to block radioactivity. So if you shielded things with lead, then the radioactivity didn't seem to go through the lead. And then he put some radioactive material in a hole he drilled into the lead. Okay, so this is a block of lead, he drills a hole and he puts some radioactive material there. And so the radioactive emissions from this, as it naturally, spontaneously decay, is going to come out this way. But the leap of ingenuity is how he actually could see radioactivity. Because remember, you can't see radioactivity. The way he saw radioactivity is he put what most people would call a piece of film. He called it a photographic plate. But a piece of film, and film, like old-fashioned film, when you had cameras that had film in them, when light hits this, or when radioactivity hits this film, it exposes, or it turns it bright white, and the other part where the radioactivity didn't hit did not turn white. So basically what he got was he got a bright spot on the film. And he was like, oh, that's great. So now I can see, quote, when the radioactivity is coming and hitting it because it's leaving a spot on the film. Okay, so then he took it a little bit further. Now you can redraw your picture if you want. I'm just going to take the original picture and tune it up a little bit. Now he said, well, I wonder if that radioactivity is all one thing, or if it consists of various different pieces that all have different charges. How could I maybe separate it? So, he used what he knew about magnetism. And he placed a magnetic field, B, remember B means magnetism, a magnetic field, a magnetic flux. And in this case, I have it drawn so that the magnetic field is pointing into the board, so it's like north out here, south is into the board. Okay, so he's got a north-south magnetism here. And so now, when the little radioactive emissions leave, they're being exposed to magnetism. Now think about what this does. Remember we learned previously with the left-hand rules that if you have a negative, like an electron, if you have a negative and you expose it to magnetism, it will actually affect the path that the negative will travel. So let's go back to our left-hand rule. Our left-hand rule says if we're going to follow a negative, it would be our thumb, and our fingers are going to point in the direction of the magnetic field, and our palm is going to tell us which way that this thing is going to be pushed. So in this case, you can see that if there's a negative, it's going to be pushed down. If negative. And in fact, there must have been a negative. Because when he put his film here, he got a bright spot down here. But he also got two other bright spots. One here and one up here. Because what happened, if you think about it, the negatives get forced down, well the positives, they get forced exactly the opposite direction. They get forced up, and anything that doesn't have a charge, no charge, neutral, hits in the middle. So what he had done is he had separated the radioactive emissions into three categories. And he called these categories alpha, beta, and gamma. Okay, beta's down here because it's the negative one, and we write it B negative. And gamma is there, it's neutral, and alpha is up there, it's the positive one. So he separated into alpha, beta, and gamma. And I guess my picture is not perfectly realistic. I shouldn't have drawn alpha up so far. I should really draw it more like that. Alpha has a little bit more mass, so it doesn't get moved as much. So it's actually not tipped up as far as the way I drew it the first time. So, for today, this is radioactivity.